Hello, and this is part 2. This is a follow-up to my earlier video where I talked about what exact differential equations are and how to solve them. So in this video, I'm just going to be going through a couple more examples to help you get the hang of this. So here we have the differential equation, e to the x plus xy squared times dx plus x squared y minus cosine y times dy equals 0. First, is this an exact equation? Let's check. So first we check to see if the partial of what the partial of m with respect to y is. So we're looking at the thing in front of the dx and taking its partial derivative with respect to y. Since e to the x is constant as far as y is concerned, its partial derivative is 0. And then treating x as a constant, the derivative of 2y would be, or of y squared would be 2y, so we get 2xy here. Meanwhile, over here, the thing in front of the dy, the n, we have to look at its partial derivative with respect to x. So the partial of n with respect to x, so now we're treating y as a constant and x as the variable, and we get 2xy minus 0. If y is treated as a constant, the minus cosine y is constant, and so its partial derivative would be 0. And these are really the same thing. They're both come out to be 2xy, so this is an exact equation. The partial of m with respect to y and the partial of n with respect to x are the same function. So, now that we know it is an exact equation, let's solve it. Let's find what the f is that this is the total differential of. So that means that the partial derivative of that f with respect to x would have to be e to the x plus xy squared. So anti-differentiating or anti-partial differentiating with respect to x, treating y as a constant, we get the antiderivative of e to the x is just e to the x. The antiderivative of x to the first power times a constant is 1/2 x to the second power times that constant. And then we add on a constant of integration that's constant as far as x is concerned, but might depend on y. So I write it as g of y, something only involving y. Now, let me just go forward from this. Remember, there's two ways you could do this. You could go backwards from what has to be the partial of f with respect to y, or you could go forwards from f itself. So I'm going to go forwards from f, take what we just got for f, and take its partial derivative with respect to y. So treating x as a constant, the partial derivative with respect to the variable y would be 0 plus 1/2 times 2 is 1 x squared y plus whatever the derivative of this is, g prime of y. And then that has to match this. They're both the partial derivative of f with respect to y. So x squared y plus g prime of y has to equal x squared y minus cosine of y. So g prime of y must be negative cosine y. And anti-differentiating that to get from g prime to g, we get that g of y is negative sine of y. Now, stick that in up here where we said that g of y goes, and we get that f is e to the x plus 1/2 x squared y squared plus negative sine y. And so we've got our solution to the differential equation given by e to the x plus 1/2 x squared y squared minus sine y equals a constant c. The end. How about another example? 3y squared minus 2x squared y times dy dx equals 2xy squared. Now this isn't set up the way we normally expect to see our exact differential equations, so let's rearrange things a bit. Let's multiply both sides by dx, and then bring everything all on the left side equal to 0 on the right side, so that it becomes negative 2xy squared times dx plus the quantity 3y squared minus 2x squared y times dy equals 0. So now it's set up in that form, something times dx plus something times dy equals 0. So now we can check to see whether this is, in fact, an exact differential equation. So we have to check to see if the partial of this with respect to y is the same as the partial of this with respect to x. So the partial of m with respect to y would be negative 4xy. And the partial of n here with respect to x would be 0 minus 4xy. So they are the same. This checks out. It is an exact equation. Okay, now that we know it is an exact equation, well, let's solve it. Let's find what function of x and y these are the partial derivatives of. Okay, so the partial of f with respect to x would have to be the thing in front of the dx, the negative 2xy squared. So anti-differentiating that with respect to x and treating y as a constant, we get that f must be negative x squared y squared plus g of y, something that's constant as far as x is concerned, but might depend on y. Now let's go forward from this. Let's take the partial derivative of this with respect to y. So the partial of f with respect to y would have to be negative 2x squared y plus g prime of y. And matching that up with the thing in front of the dy, because that's supposed to be the partial of f with respect to y, we get that negative 2x squared y plus g prime of y equals 3y squared minus 2x squared y. They both agree about the negative 2x squared y, and the other part has to match up as well, so g prime of y must be 3y squared. So we can just anti-differentiate that. If that's what g prime is, then g would be the antiderivative y cubed, plus possibly a numerical constant, but that's going to show up when we write our solution. So stick y cubed back in here for g of y, and now we know what f has to be. It has to be negative x squared y plus y cubed, so the solution to our differential equation is negative x squared y squared plus y cubed equals c. Again, that's not solved for y, but it does give us what y is implicitly defined as a function of x.